All right, so what we're looking at today is deposition. Deposition. Okay, so what you should already know is that weathering is a process that rocks break into smaller pieces. Erosion is a process when those little pieces are moved, all right? Well, they don't stay moving forever. At some point, those moving particles are going to get dumped in a new location. And the dumping of those particles in a new location is another process, and that is the process of deposition. So deposition is a process by which transported materials are left in a new location. And another word that's sometimes used for deposition is sedimentation. So basically means the same thing. All right. Now remember, there's different ways in which particles can get transported. Just using a stream, for example, solid particles, deposition occurs when the solid particles are released by the agent. Now what I mean by agent is one of the agents of erosion. So wind, water, glaciers, things like that. So like just using water, for example, moving water is an agent that is moving the particles. At some point, that water basically kind of lets go of those particles and they settle out. That's when deposition happens, all right? Now, what precisely would cause a particle to settle out, we'll look at in a little bit. But that's what happens for solid particles. Now for dissolved materials, like for example, salt and water dissolves and chemically becomes part of the water. How that gets deposited is when it precipitates out as a solid. Now normally when you hear the word precipitation, what you normally think of is rain, right? Well, what precipitation really kind of means is like to come out of. So like when you're dealing with weather, precipitation is the moisture that's coming out of the sky. In this case, what I'm talking about is the solids that are coming out of the water. So a good example of this would be like if you have some salty water, like when during the winter time, when you have that salty slush that your car drives through and that splashes up on your car, and during the course of the day, when that stuff evaporates, the water evaporates up in the sky, but the salt gets left behind. So you get this like layer of salt on your car. That's kind of like what's going on here, all right? As that salty water evaporates, the minerals precipitate out. They come out of the water and get left behind. Now, same thing happens if you go to swimming in the ocean. When you go swimming in the ocean, a lot of times there's a shower there. When you get done swimming, you're supposed to go and take a shower afterwards. The reason being is when you're swimming in salt water, if you don't take a shower afterwards, what's going to happen is you have that layer of salt water on your skin, and when that salt water evaporates, it basically leaves like a little crusty layer. The water evaporates, but the salt gets left behind, so you get like a crusty layer on your skin. It's kind of doesn't feel very good. All right, so that's how you can get another form of deposition. Now, with your skin or with your car, it's just like a little tiny layer of salt. But just imagine, if there was a sea that was 200 feet deep and it had 200 feet of water that was evaporating, and that salt starts to come out of it. That's going to be not just a thin layer; it's going to be a nice thick layer of salt. And it's not just salt. There's other minerals that do that. There's other rocks and minerals that do that as well. But I just use salt as an example. All right. Now, some of the factors affecting deposition. All right. Stream velocity. When a stream slows down, deposition occurs. All right. So from the last topic, you should know that a faster stream goes, the more different sized particles it can carry. When a stream slows down, those particles that it was carrying, if it stops, then all those particles just come out of the water. But if a stream slows down, what's going to happen is the stream's going to start dropping particles one by one according to their size. Now, I can show you that chart that we looked at in the last topic. All right, so I showed you this chart in the last topic. So for example, let's say there was a stream that was traveling 200 centimeters per second. So if it's traveling 200 centimeters per second, what that means is it could carry cobbles. Now, it doesn't mean it carries only cobbles. What that means is cobbles are the biggest particle it can carry. If it's traveling 200 centimeters per second, it's carrying cobbles, it's carrying pebbles, it's carrying sand, it's carrying silt, it's carrying clay. It's carrying all those particles, all right? Not fast enough to carry the boulders, but it can carry everything from the cobbles down. So let's say the stream slowed down from the 200 right there, and let's say it slowed down to 10, all right? Let's say it slowed down to 10, all right? Now, as the water's slowing down, basically you're going from that part of the chart to this part of the chart. As it's slowing down, what's gonna happen is, eventually, first off, as it's slowing down, the cobbles are the biggest particles, so they're gonna get deposited first. And then as it slows down some more, what's gonna happen is all the pebbles are gonna get deposited. So if it's slowed down from 200 down to 10, it would still be going fast enough to carry the sand, the silt, and the clay, but it's not fast enough to carry the cobbles and the pebbles. So the cobbles and the pebbles would get deposited, right? So that one and that one will both be gone. It's still carrying these guys, but those guys get deposited if it went from 200 down to 10. Right? So that's basically how deposition works. As the stream's slowing down, gradually the bigger particles get deposited first, and then the smaller particles. All right, now, where do streams slow down? So when streams slow down, they start depositing material. Where do they slow down? Well, one of the main places they slow down is streams slow down when they enter large bodies of water, right? So like when a stream enters into a lake or a river enters into the ocean, what you have is water that's moving, so it's carrying a bunch of particles, but then it basically stops when it hits the larger body of water, so those particles it was carrying start to come out of the water. So you have lots of deposition taking place where streams or rivers enter larger bodies of water, like a lake or an ocean or a sea or something like that. So you get lots of deposition taking place there. Now, something else that affects the deposition are sometimes it's the particles characteristics itself. So different characteristics of particles can cause it to deposit at different rates. So we're going to do a little demonstration experiment thing right here. And right here, we'll look at a few factors. All right, so I have a tube full of water here, And we're going to look at how different materials settle differently. All right. Now, first off, let's look at the size of a particle. All right. So right here, I have two balls of clay. They're both made of the same original clay, so they're both the same material, but what's different about them, here I have a small piece, and here I have a big piece, and they're both fairly round. So the only thing really different about them is their size. So we want to see how does the size of a particle affect how it gets deposited. All right. Well, I'm going to drop it in there. I'm going to start timing when it gets there, stop timing when it gets there. All right. So for the big one, all right, so the big one took 1.34 seconds. The big one took 1.34 seconds. All right. Now, I'm going to drop the little one. The little one took 2.09 seconds. So you can see that different sized particles cause it to settle at different speeds, right, in different times. Right, next, what we're going to look at is different materials that have different densities. So here I have a little piece of that clay again, and here I have a little piece of the mineral galena. Now, galena, the chemical formula for galena is PBS. That means the PB stands for lead. So galena has lead in it. So galena is a very dense material. So as something that has a relatively small density compared to something that has a really big density. All right. So first I'm going to drop the piece of clay, so the small density. And that took 2.01. Right. And now I have the piece of galena, which again has lead in it, so it's very dense. And drop that in there. All right, and that was 0.51. 0.51. All right. And the last thing we'll look at here. All right, so I have two pieces of clay. Now they're both originally about the same size, but what I did is one of them I kind of balled up, and the other one I flattened out. All right, so we want to see how the ball settles compared to the flat one. All right. So again, the round one here, I'm going to drop in there. And took 1.39 for the round one. And now for the flat one. .57. All right. All right, so here's our results. All right. So for size of particle, what you should get out of there is big, settles faster, lower settling time. Okay. Small, settles slower, and it has a greater. Is a greater settling time. All right. So on my graph over here, what I should have noticed is the big particle had a small time and the small particle had a big time. So on my graph here, the big one had a big time, or excuse me, the big one had a small time, the little one had a big time. So my graph went up like this. All right. Density of particle. All right, so the low density one had a settling time of 2.01 seconds. The high density one had a settling time of 0.51 seconds. So that means the high density one settled faster than the low density one. So for density of particles, the denser it is, it's going to have less settling time. And that means it's traveling faster. All right? So the denser it is, the faster it goes, the less time it takes. So on my graph over here, the more dense it was, the less time it took. So on this graph here, that'd be a graph going down. The more dense it was, the less time it took. All right? Now for the shape of the particle, what you should have seen is that the flat one took more time and traveled slower. The round one took less time and traveled faster. So round settles fast. Took less time. Flat settles slow, took more time. Okay. So if I was going to plot this on the graph here, let's say I was going from round to flat, all right? The round one took less time, the flat one took more time. So this graph would go up like that. So size of particle, density of particle, and shape of particle are the three factors that affect how fast it takes or how much time it takes a particle to settle. Now, on these graphs here for deposition, what you got to be really careful about is a couple things. First off, you really want to pay attention to what the scale says on the bottom here. Because I set it up with the big particle here going from big to small, all right? But I just as easily could have done this x-axis going from small to big. So if it went from small to big, the line on my graph would have done the other thing, gone the other way, all right? Just like down here, I mean, I went from round to flat. I just as easily could have done the scale down here going from flat to round. If it went from flat to round, then instead of my graph going up, my graph would go down. So you really want to pay attention to what's on the scales. But the other thing, the thing that you probably need to pay extra attention to is what it says on the side here, all right? Settling time or settling rate, all right? Now, in this example here, all three of these graphs said settling time, all right? However, for example, for this guy right here, right? So what we plotted was basically the time. So the more dense the material, the less time it took to sink. However, if I was plotting the rate, which is the speed it's traveling, then the denser it was, the faster the rate it was traveling, all right? So you gotta be really careful on these, whether it says settling time or settling rate, because if something travels at a very high speed, if it travels at a very high rate, then it's gonna take a small amount of time to get there. So the graphs are gonna be reversed. So with this one, the settling time graph would go down, but its settling rate graph would go up. So you really got to pay attention to what those say on the side there. All right. Anyway, so that's deposition, what deposition is, and some of the factors that affect